Ever wonder how a drone navigates through a dense forest or a self-driving car, avoids obstacles in a bustling city? It's not magic, it's visual localization, a cutting-edge technology that lets machines see and understand their surroundings. Today, we're diving into a groundbreaking study that's redefining this field, from AI-powered puzzle solving to 3D maps that adapt to the real world. Let's break it down. Imagine you're lost in a maze with no GPS. Your brain uses landmarks, shadows, and patterns to figure out where you are. Machines do something similar, but with a twist. They analyze images to match locations, like solving a puzzle with missing pieces. But here's the catch. In complex environments, think crowded cities, disaster zones, or dense forests, traditional methods often fail. That's where Hi2-GSLoc steps in, a breakthrough from Krishnan et al. That's rewriting the rules of robotic navigation. So how does it work? Let's start with the problem. Traditional visual localization systems struggle when scenes lack distinct features or change dramatically between views. For example, a drone flying over a forest might capture images that look identical to a ground-level camera, causing confusion. Hi2-GSLoc solves this by combining two powerful innovations, 3D Gaussian Splatting and a Coarse-to-Fine Refinement process. First, 3D Gaussian Splatting. Think of this as a digital 3D puzzle. Instead of using traditional 3D models, which are data-heavy, Hi2-GSLoc represents scenes as a collection of 3D Gaussian distributions, mathematical shapes that encode both geometry and appearance. Each splat holds position, color, and opacity, creating a compact, detailed representation of the environment. This allows drones and robots to process vast scenes without overwhelming their processors. Next, the Coarse-to-Fine approach. It's like solving a puzzle in stages. The system first identifies rough landmarks. Think of it as using a compass to get your general direction. Then it zooms in, refining those guesses with a technique called C.R.A.S. Consistent render-aware sampling. This method prioritizes features that are stable across different viewpoints, like the edges of buildings or the texture of tree bark. By focusing on these reliable clues, Hi2-GSLoc reduces errors dramatically. But here's the real magic, dense matching. Once the system has a rough estimate, it generates a detailed 3D map by rendering depth, color, and textures from the initial guess. This is where Gaussian-based features shine. Unlike traditional models which struggle with aerial perspectives, these features adapt to any angle, ensuring accuracy whether the camera is on the ground, in the air, or at an extreme tilt. The results? In real-world tests, Hi2-GSLoc achieved a median error of just 17.2 cm. So precise, it's like measuring a soccer field with a ruler. On datasets like Mil-19 rubble, disaster site reconstructions, and Xi-MSTS urban environments, it outperformed all competitors, achieving 100% recall in scenarios where others failed. This isn't just about accuracy, it's about reliability. Whether it's a drone delivering supplies to a remote area or a robot exploring a cave, Hi2-GSLoc ensures they stay on track, even when GPS is unavailable. So what's next? Hi2-GSLoc's efficiency makes it ideal for edge devices with limited computing power, opening doors for real-time applications in agriculture, search and rescue, and augmented reality. But the implications go deeper. By bridging the gap between 2D images and 3D understanding, this research could revolutionize how machines interact with the world, making them not just smarter, but more intuitive. The next time you see a drone or a navigation app, remember, behind the scenes, scientists are working to make sure those digital guides are as sharp as possible. And with systems like Hi2-GSLoc, the future of location tech is looking pretty precise.